Hello everybody. Today we've got a lot to go over, so I'm just going to jump right into it. We're going to be talking about radicals today. Now, some of you might be wondering, what on earth is a radical? I've never really heard of the term radical, but I promise you've dealt with them before. So, the origins of the radical. So I'm going to start out with talking about what they are and then where they were derived from. So let's start with a triangle. I know everybody last year got to this because I know I taught it to you. Let's say that we have a triangle with this length is 3 units. We'll just say 3 units. We're not in geometry. We don't have to be specific, but we have a, and then we'll call that side x. So we have a triangle. It's a right triangle. So let's say that we get everything proper. Some of you are probably already screaming at the camera, saying, or at your screen, saying that I know exactly how to find that x. Well, good. I'm glad you know how to find that x. So, but the reason that I'm going over this is because it'll lead us into radicals, what they are. So we know that a squared plus b squared, a squared plus b squared equals c squared, but in this case I'm going to say x squared because the x is in the c position. All right, so we're going to go ahead and plug some things in here. So we have 3 squared plus 4 squared equals x squared. Okay, well 3 squared is 9 plus 16 is equal to x squared. And then 9 plus 16 is 25 equal to x squared. Now, last year I taught you a way to get the x by itself. So that's pretty much what we do in algebra, is we try to get a variable by itself, at least at this level anyway. So how would we get the x by itself? Well, let's assume that you don't know what you think that you're using for this. We're going to use our exponent laws. So we're going to use exponent laws down here. We'll say exponent rules. Now, knowing what we've learned in the last video, the last couple videos really, how would we find that x? Okay, well, we would take, so we have 25 is equal to x squared. Now I know that there's a way that I can make that a 1, because if x by itself is x to the first power, so I'm wanting to get that x to 1. So how would I do that? Well, 2 divided by 2 is 1, or 2 times 1/2. Same for here, 2 to the 1/2 power. Okay, so now we have 25 to the 1/2 power is equal to, well, the 2 in both of these cancel, and we're left with x. Well, what is 25 to the 1/2 power? Well, that's where we get into radicals, and we know these as square roots. So this is the same as, so we'll say 25 to the 1/2 power is equal to the square root of 25, which is equal to, I'm going to write it down here, which is equal to 5. Now that was a funky shape. There we go. All right, so that is the reason why, that is the origins of the radical. So we got to a point where we found that this number times itself is another number. But we wanted to find out what those two numbers that multiply to give us this number. So, so believe it or not, geometry is where we started realizing that we needed the radical, or the root. So let's move on. We'll start talking about square root, or the nth power. Okay, so we just went over above that x to the 1/2 power is equal to the square root of x. Okay, and now the same thing goes for the nth root. So x to the 1/n is equal to the square root, or not the square root, the nth root of x, or the base. Now I'll go ahead and give you an example of both of these. We'll say because we'll say 4 to the 1/2 power is equal to the square root of 4, which is equal to 2. Now we'll do 16 to the 1/4 power is equal to the 4th root of 16, which is equal to 2. Okay, so those are our examples. So we'll go ahead and mark that as examples. So that's what a square root is. A square root is essentially a fractional exponent, but we didn't want to deal with fractional exponents all the time, so we made a way to make it whole numbers. So these are whole numbers. So the same thing with a division. Division is purely foundationally, it's just multiplying by a fraction is what division is. So a square root is the same thing. It's an exponent to the 1/2. It's a fractional exponent. So a number to a fractional exponent. But we didn't want to deal with fractions, so that's the reason why we came out with the root concept. Well, let's start talking about some rules and properties of square roots. So our first, to our radicals, our first rule here is the product rule. Now, similarly, if I have x to the nth power, let's write this as 1/n times x to the 1/m. Well, this is equal to, let's not worry about square roots yet, is equal to x to the 1/n plus 1/m. Now, let's think about this as square roots. So, we'll just say square root, because most of what we'll deal with is square root. Since square roots are the same exponent, so let's say x to the 1/2 times x to the 1/2 is equal to the square root of 2, or not square root of 2, square root of x times the square root of x, which is equal to x to the 1/2 plus 1/2, which is equal to x. So if I have, let's do an example of that. Let me change the color of these to make it a little bit more accessible. Change that to red, and in our example, we'll stay blue. All right, so an example of this, we'll just use 4. 4, square root of 4 times the square root of 4 is equal to 2 times 2, which equals to 4. And if you notice x there, our value x was our original, it came up to 4. Now, the purpose of this is to show you that you can break apart square roots under multiplication. So here's another example. Let's take the square root of, let's say, x times y. Well, this is equal to the square root of x times the square root of y. Yeah, so under multiplication, we can separate these into different square roots, and this comes in handy. Let's say that I have, let me separate this here, write another example. Let's say that I have the square root of 16 times x squared. Well, this is equal to the square root of 16 times the square root of x squared, which can be simplified to the square root of 16 is 4 times the square root of x squared is x, which is equals 4x. So you can now see the value in this, being able to separate this into multiple different functions. Now let's move on to the quotient rule. I'm going to write the rules out here in red. So the quotient rule says, let's say that I have, let's write it in black because this is a rule. Says that, let's say I have a square root of x over y. This is the same as the square root of x over the square root of y. Now, let me show you when this would be handy. So you have the square root. Stay consistent. Say that I have a square root of x squared over 4. Well, this is the same thing as the square root of x squared over the square root of 4, which is equal to x over 2, or 1/2 x, however you want to write it. But now you're starting to see the purpose of the reason, or the purpose of why we do these kind of things. All right, so let's move on to rationalizing the denominator. Oh, this is good, especially right after quotient rule. So let's say that the bottom isn't as nice of a, let's say that the bottom, the denominator of the fraction, we have numerator and denominator on the bottom. Say the bottom of the fraction is not as nice and as clean as square root of 4. So we know that we're going to end up, once we simplify it, that there's going to be a square root in the bottom. Well, then we can't leave the square root in the bottom properly. It just doesn't look right. So what we do is we have to rationalize the bottom, and I'll show you what that means. So the rule, so I'll just go ahead and write this out. I'm going to write it in red to show how important it is. Rule says roots or radicals. I'll just say radicals. I'll say roots. Roots are not allowed in the denominator and I'll say right here bottom of the fraction. Okay, so now I'm going to jump on to an example. So let's say we have a square root. Let me make this a little bit more formal. Say we have a square root. The top, we'll just say A is x squared, and in the bottom we're going to say is, we'll say 5. Okay, so the square root of x squared over 5 is equal to, according to our quotient rule, we divide it into square root of x squared over the square root of 5, and then square root of x squared is x over the square root of 5. Now, there's a problem with this. The square root of 5 gives us an irrational number. So we talked about irrational numbers in our first video. The irrational numbers are numbers that are non-terminating. So like pi would be an example. The number e, which we'll get into when we get into logarithms, is an example. So such as if I was going to say 1.456232142, and it just goes on forever without repeating, we're going to have some rounding errors whenever we deal with that. But if we keep it as a square root of 5, it maintains more of, you won't have a rounding error if you keep it in its square root formatting. So like the square root of 2 is an irrational number. Square root of 5 is an irrational number. Pretty much, if you can't, if it's not a perfect square, so 4 is a perfect square because the square root of 4 is 2. 9 is a perfect square because 3 times 3 is 9. 16 is a perfect square. 4 times 4 is 16, so 4 squared equals 16. Unless it's a perfect square, you can't write it as a rational number. All the other numbers are going to come out as an irrational number. So we're going to keep them in that form. So square root of 5 is going to be irrational, but we're going to leave it as a square root of 5. Now we also have this rule hanging over our head that says that we cannot have a square root in the bottom. So what are we going to do? We're going to multiply this number by 1, or square root of 5 over square root of 5. So we talked about in an earlier video, any number over itself is equal to 1. So we just multiplied it by 1. That's all we're doing. But this is going to give us a little bit different of an answer. So when you multiply fractions, you multiply straight across. So x times square root of 5 is going to give us square root of 5x over square root of 5 times square root of 5 is, well, 5. Let me write these a little bit neater. So this would be a correct answer there. Let me do another example to kind of show you why you would want to do this. Okay, so let's say that we have the square root of, we'll say 4 on the top, and then we'll have an x on the bottom this way. So this is going to be the square root of 4, not 9, 4 over the square root of x. Square root of 4 is 2. Square root of x is a square root of x. We don't know what the square root of x is. It could possibly be a rational number, but most likely, because there are more irrational numbers than rational numbers, kinda. I mean, whenever we're dealing with affinity, it's hard to deal with. But if I'm going to count from 1 to 10, or even 1 to 100, there's going to be more irrational numbers between those two boundaries. That's what I'm meaning by it. So we have to rationalize the denominator. Well, how do we do that? We multiply by the bottom. So, but the top has to also be the same. So square root of x times square root of x. Now on the top we get 2 times the square root of x, because we're just multiplying straight across. And on the bottom we get, well, x. And that is a perfectly appropriate. Now, we could have written it as 2x to the 1/2 over x. But if you notice, if we do 1/2 minus 1, we're going to end up with another root in the bottom. So it's perfectly proper to leave square root of x and an x in the bottom, which is counterintuitive to the exponent rules that we learned last week. But it's perfectly okay to have a square root of the same base in the top and a base of a different without the root in the bottom. Okay, so now let's talk about nth roots. So nth roots are kind of funny. Let's see if I have, yeah. Nth roots are whenever it's a square root. So let's say rule. So here we go. N is equal to 2. Let's say, what is this? X to the n up here. And then I want to put a colon here, and then n is equal to 2. Now what this is saying is that x, let's write 1 over n. N is equal to 2. So that means that x is over 1/2. Let me write that a little bit nicer. X is equal to 1/2, which is equal to the square root of x. Now on square roots, we don't have to put a number there. We don't have to put that 2 there. That 2 does not need to be there because it's understood that a 1th root would be 1 over 1. So then you're just left with, would be 1 over 1. So you would be left with just 1, so it'd be x to the 1 with power. So a 1th root is the same as 1 as the exponent, so there's no purpose for it. 0 would give you, a 0th root would give you an undefined because it's 1 over 0. We can't divide by 0. Well, you know, it leads to an undefined answer. But let's say that in, let's write this out again. Let's say that n is greater than 2, such that n is equal to 3. So now this leaves us with x1 over 3 is equal to x to the 3rd root. So we're taking a 3rd root of x. And maybe if I write it one more time, x to the 1 over n, such that n is equal to, let's do something weird like 37. So that means x would be 1 over 37. Let me write that as an equal sign, which is equal to the 37th root of x. So if you're kind of getting the gist there, an nth root, these are, you're taking, it would be, all right, I'm going to write this in red. This means that some number cubed is equal to some number cubed is equal to the cubed root of x. So that means that, like, the cubed root of 8, let me write this as an example over here. The cubed root of 8 is equal to 2 cubed, which is equal to, oh, it's not equal to, the cubed root of 8 is equal to 2. Because, well, it's equal to, all right, yeah, that's how we'll do it. That's how we'll write it. We'll do the cubed root of 2 cubed, which is equal to 2, because 8 is the same as 2 cubed. So if you notice right there, these two are equal. Let me make that a little bit neater. 2 cubed is the same as 8, but the cubed root of 2 cubed is equal to 2. So that would be our answer to a cubed root. Let me do another one. Let's say we're going to do a 4th root of 16. Well, this is equal to the 4th root of 2 to the 4th, which is equal to 2. Now, when you have a 4th root, so I'm going to write this as a note. Whenever the exponent of the base is equal to the root of the radical, then you can cancel them out. So I'll write that out. So x to the nth raised to the nth power, that cancels with that, and then you're left with x. Okay, so let's leave that as a note, and we'll go from there. All right, so we got one more property to go over, and then after that, I'm going to leave you with a little note. Then I'm going to leave you with a question, and you'll have to answer that in your homework. So fractional exponents. Let's say that I have x to the m over n. All right, so we've just learned that x to the m over n, this would be the same as x to the mth power times, no it wouldn't. This is the same as the nth root, because we've learned at the bottom of the fraction is the root. Nth root of x to the nth power. Oh, okay, I'll write it like that. So whenever we did this is x to the nth raised to the 1 over nth power. And when you multiply those, we just learned that the nth root means that this is the nth root there of x to the nth power. Now let's do an example of that. Let's say that we have, let's say that we have 16 let's see if this will work. 3, this is equal to the square root of 16 to the 3rd power. All right, so I don't know that one. So I'm going to type it in my calculator. 16 to the 3rd power is equal to 496, and then the square root, 4096 is equal to, so I'm gonna try it, see what happens. Square thousand. Ooh, 64. I thought that would come out nicely. Doubted myself. All right, so that's how it works, is that the top number is, so if you have a fractional exponent, the numerator of the exponent is going to be what is inside of the exponent raised to that power, and then the root will be the denominator, the bottom number. If you have any questions on that, feel free to email me. I hope that this is enough. Now, I'm going to show you real quickly what all of these things are called. So I'm just going to leave this as a square root because mostly what we're going to deal with is square roots. These have different names. Like all the parts of a square root has different names, kind of like how a fraction has the numerator, which is the top number, the denominator, which is the bottom number. They each have different names. Well, same for square roots. This right here, the line, the actual root that's being taken, the operation that's being taken on the value, is called the radical. So whenever we're talking about radical expressions, that's the reason why, is because the operator is a radical. Okay, now the number that the radical is operating on is called the radicand. And then the overall, I'll write this in pink, the overall thing the entirety of everything, so the radical and the radicand, is called the radical expression. And so whenever you hear the phrase radical expression, you know that there's going to be some sort of root in there in some form. So I'm going to leave you with a question. Now, the question is, what is the difference between we'll say an expression and an equation? Now that's your question. There will be a spot in Google Classroom for you to answer that. If you're having a difficult time understanding the question, feel free to email me. But that's all I have today. Assignment 4 is already posted, and email me if you have any questions. I'll also be doing Google Meets tomorrow. Thank you for watching the video. Thank you for your patience, and I'll see you in the next video.